Hola, 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 mis estudiantes. How's everyone doing in video land? We're going to check out another dynamics problem, specifically a curvilinear motion type of problem today. It is problem 12-149, found on page 66 from Hibbeler's 13th edition textbook titled Engineering Mechanics Dynamics, copyrighted in 2013. And here's a little schematic of what we're talking about. We have two particles, A and B. They're beginning at the origin, O, and they're traveling with constant speeds but in opposite directions as depicted in this little schematic. Particle A is going to go at 0.7 meters per second in that circular path, having a radial dimension of 5 meters. And particle B is going in the opposite direction with a speed more than double particle A's at 1.5 meters per second. And specifically at a time of t equals 2 seconds, we want to find the following 3 points. Point A, the displacements of each particle along the circular path. Point B, the position vectors of each particle. And then C, the shortest distance between the two particles. Okay? As you know, I like to do a little diversion with a side note whenever I can. And I had to think real hard about this one because I was like, circular motion and scripture, how do these two tie in together? And I came to this verse. This is a verse penned by the wisest person who ever lived, King Solomon, written in his book titled Ecclesiastes. It is taken from chapter 1, verse 9. I am reading from the New Living Translation. It reads, "History merely repeats itself. It has all been done before. Nothing under the sun is truly new." And how true that is. Put another way, we might say that which was is that which shall be in the future. All right. The famous philosopher, the late philosopher George Santayana, said it quite eloquently, taken from volume 1 of his work titled The Life of Reason, or The Phases of Human Progress, published in 1906. George Santayana lived between 1863 and 1952. A Spanish-born American author and philosopher said, "Those who cannot remember the past are condemned to repeat it." That is really very well put. I even shudder in the times that we're living in for those who don't take time to study a little bit from the past and the historical facts and how those things rear their ugly heads once again in today's world. Especially that is true of today's world, where we have so many things that we can point to. And speaking of which, let's take a look scripturally. I have so many that I can pull out, but I'm only going to limit this to 3 because of time constraints. But like I said, we could literally talk and talk and talk from scripture and bring out lots of things from scripture that we can see things repeated from. Well, one of them is this one. It's taken from the book of Genesis, chapter 22, verse 6, reading from the English Standard Version. It says, "And Abraham," Genesis 22:6, okay? "And Abraham took the wood of the burnt offering and laid it on Isaac his son." Now you may say, well, how is that something that's been repeated? So that is that which was, that's the was part, is that which shall be. That's something that's going to come in the future. And scripturally we see a beautiful picture of this in Jesus, right? Because God the Father took the crossbeam of the cross that Jesus died on, laid it on his back, and Jesus actually carried that crossbeam on his back as he was going up to Calvary, where he would be the sacrifice that would end all other sacrifices. Because as you know, historically, the Jewish people always did animal sacrifices to pay for the sins that they had committed. And well, Jesus paid it all. He did that one and end all sacrifice on Golgotha's hill when he died on the cross. So that's a beautiful point. Another one is, again, from the book of Genesis, specifically from chapter 6 through 9. There you read the account of the worldwide flood, and God told Noah, this man named Noah, go ahead and build an ark. And here is Noah working on this ark for a very, very long time. I believe it was something on the order of 120 years. That is a really long time to be building a boat. And And, well, you know what? He was building this boat. He was being obedient to the word of God. God said, I'm going to destroy the whole world, basically press delete and start all over again, because humankind had become so evil. And so here's Noah building and building away, and all of his neighbors and the locals are coming by and basically mocking him. They're laughing at him. They're saying, "Well, what are you doing? You've lost your mind." Basically, we don't have any water. We don't have any flooding, and they all laughed. Well, lo and behold, after a good century, 120 years of this, the rain started coming. The only people who survived that, as you probably know the story, were Noah, his wife, his 3 sons, and their 3 wives. And then, of course, the animals that they brought aboard. All the other animals, all the other human beings in the whole world perished in that worldwide flood. And you may say, well, how is that a picture of what is to come? Well, we know that Jesus is going to return. He said so. He made that very clear. He said, I'm going away. This is when he was just about to ascend into heaven. But I'm going to come back. So we definitely know that Jesus is going to return. And those of us who are wise will know that Jesus is a picture of that ark. Whoever is aboard Jesus is safe. Whoever is not on board with Jesus is not safe. So again, I would point you to check out my video titled One Question to get a little more information on that. All right, and let's see. There is one other thing I would say, and that is with regard to Jerusalem. And Jerusalem is all over the news today. As a matter of fact, it would not be incorrect to say that Jerusalem is really, really, really the epicenter of all the focus of the whole world and the news. And here is something that John the Revelator said. He says in his book, Revelation 21:2, taken from the Jubilee Bible 2000 edition, "And I, John, saw the holy city, the new Jerusalem, coming down out of the heaven, prepared of God as a bride adorned for her husband." You see that the new Jerusalem is descending upon the earth and going to basically sit atop the old Jerusalem. And so, all of this comes together, my friends. It's what was is what is going to be again. And I will leave you with these verses written by the disciple Peter in his second epistle, chapter 3, verses 3 and 4, taken from the New Living Translation. Verse 3, "Most importantly, I want to remind you that in the last days scoffers will come, mocking the truth and following their own desires." Verse 4, "They will say, 'What happened to the promise that Jesus is coming again? From before the times of our ancestors, everything has remained the same since the world was first created.'" I hope that you will not be a scoffer, a mocker, but do take it seriously that Jesus is the only way. Alrighty. Again, check out my video titled One Question. I'm going to do this problem in a somewhat circuitous fashion. Sorry for the pun. But I would like us to glean some important things from this problem that I could bypass all of this and cut right to the chase, and we could be done with this problem pretty quickly, but I think at the expense of some learning. So let's take a look with, specifically I'm going to point out 3 things as we go through this problem. One is a kinematics thing that I'm pretty sure all of you know. Another is the geometric argument that, again, we've talked about in many, many past videos. And then we'll bring out something from a dimensional analysis standpoint, and then we'll try to tie everything together to show how all of this truly does come together. Before I do that, let me go ahead and write out what is given here. I always like to start my problems this way, and I would urge you to try and adopt the same approach. List what is given and do it symbolically so your eye and your hand and your brain are all coordinated with what's going on. Because if you don't do this, at least for me, the problem can kind of get lost in translation. So we have a circular path, and it has a radius of 5 meters, right? And we'll write that symbolically as r equals 5m. M is meters. And we were also told the speeds of those particles, so v sub a is 0.7 meters per second. And we were also told that it's a constant. All right, and I guess we weren't told that it was a constant, but I should write here with constant speeds. All right, so I apologize for that omission, but I think that is actually written in the problem statement from Hibbeler. And then V sub B is going at more than double the speed of A. It's at 1.5 meters per second. It's also a constant. And here are the things that we want to find. We want to find, in part A, we want to find the displacements. Okay, I will denote these as S sub A and S sub B. And, well, S sub A is really the arc length, okay? So don't get too confused, but that's in keeping with the symbols that Hibbeler himself uses in the book. This is the arc length. And I might denote it in other places, but not really here. I might denote it as, let's say, A with that little arc above it, sub A. But I'm not going to do that here. I'm going to just call it S sub A. Well, in picture form, it's going to be this little segment there in the circle. So this is the S sub A. Okay. And, well, that's part A. Part B, we want to find the position vectors. And the position vectors we can denote as R with that vector symbol overhead sub A, and R with the vector symbol overhead sub B. No problem. And then C, the shortest distance between the particles. And we might call this R sub AB, and you'll see what I mean by that in a second. Okay, so, well, let's go ahead and start. Again, I'm going to do this in a kind of a belabored fashion, but the hopes are that we don't lose some insights as we go along. So let's go ahead and look at kinematics first of all. By kinematics, I believe we all know that the speed is equal to let me just do this generically first. The speed is equal to omega times the radius. We all know that from a kinematic standpoint. And so I can back solve for omega. This omega is the angular speed, right? Angular speed. Right? So omega is equal to V over R. And so if I do that, I can find that omega A is equal to VA over R. And I know what VA is. It was given as 0.7 meters per second, and R was 5 meters. And lo and behold, the meters on the top and on the bottom cancel, and we're left with a value of 0.14 radian per second. Okay, 0.14 rad per second. I can do the same thing for omega B. The angular speed of particle B is its speed, V sub B, over the radial length of 5 meters, and its speed is 1.5 meters per second over 5 meters, and you do that and you find that this is 0.3 rad per second. Well, okay. Now, if you want, and this is just kind of a aside, but let me do this. Again, the whole idea here is not just to solve a problem. We could do that real simply, but I want us to get some deeper understanding here. So, as an aside, I could say that omega A, you've probably heard of the units of RPMs. Well, let's check out what that would be. We know what it is in terms of radian per second. It's 0.14. But omega A, the angular speed of particle A, is 0.14 rad per second. Now, I'm going to ask you all, how can I convert this into revolutions? Well, we know that there are 2 pi radians per a single revolution, right? In other words, a particle will go one full circle in in terms of the angular measure of 2 pi radians. Okay, and when it goes around one full circle, that's what I mean by 1 rev. So notice what we have here. We have the rads canceling from top and bottom, and we're going to have a value of, if you crank that out on your calculator, 0.02228 revs per second. Which, if you now, well, what is this? How about RPM per minute? Well, we know that there are 60 seconds in a minute. So if you were to multiply this value right here by 60, you can also write this in terms of RPM. And that's going to be 1.3369 revolution per minute. Or I could say that is just RPM. That's kind of an aside, and it's good to know all of that stuff. You may or may not know that. I'm not sure, but it's good to know nonetheless. Well, that was kinematics. Let's check out something from geometry, and we've talked about this geometry concept in past videos, so if you have been following my videos, you probably know this already, but the arc length S, let's say S sub A, is going to be the radial amount times the included angle, alright, theta A. Alright, so, well, from here, I can say that if I were to solve for the angle, theta A is equal to S sub A over R. And now, I'm going to say, by a dimensional analysis approach, alright, so, well, let me just finish this. Let me also do the S sub B part. So, S sub B is R times theta B. And so we get that theta B is equal to S sub B over R. And now I'm going to check out something from a dimensional analysis approach. So by dimensional analysis, this is something maybe we haven't talked about in my videos at least. And maybe you know this already, maybe you don't. But what is theta A? Theta A, if we're to talk about this has got to have some sort of either units of degrees, or it's got to be expressed in terms of radians or something along those lines. It's an angular measure, right? It's an angle. Well, how can I get that? Would you not agree that this has to equal, from a dimensional analysis standpoint, omega A times the time? Let's see that. Omega A is going to be expressed in some angular measure, let's say radians per second, like we just did up above, times the time is seconds. So the seconds on the top and bottom cancel, all right? And, well, I think you would agree that you're left with an angular unit there. It's radians. And so let's do that. In 2 seconds, let me say in t equals 2 seconds, I can say that theta A is omega A times t. It is 0.14 radians per second times 2 seconds. Again, seconds cancel on the top and on the bottom, and you're left with the angular measure. And you see that, well, this is 0.14 times 2 is 0.28 radians. I myself can't really visualize what a radian is, or 0.2 radian. I can't really visualize that. So let's convert that to degrees. How do you convert radians to degrees? We know that there are 2 pi radians in 360 degrees. So if you multiply 0.28 times 360, and on the bottom you divide by 2 times pi on the bottom, you're going to get, on your calculator, 16.04 degrees. I can visualize 16.04 degrees a lot better than I can 0.28 radians. Let's do the same thing for theta B. In the interest of time, let me kind of just do that real fast. So it's omega B times t, and this is going to come to 0.6 radians, which works to 34.377 degrees. Okay, so I can visualize those things better. Now, here's the point that I wanted to do after all this circuitous discussion. I wanted to show that you have this theta theta A, which is this guy right here, I'm going to do this in a different color so you see it, is equal to this theta A. Okay, let's go ahead and check that out real fast. So therefore we have, symbolically we have S sub A over R is equal to omega A times T multiplied through by the R, so I get S sub A is equal to omega A times that R times the T. What is this? Omega A times the R is what? We just talked about that. I hope you see that that is really the speed of particle A, V sub A. That's the kinematic relationship. So really, all this to basically come to something that we could have jumped right into from the beginning and say that. Okay, so well, now that we know that relationship, let's go ahead and actually solve the problem. Okay, so I hope you're not too disappointed that we took this long route, but I hope that you learned something from that, maybe that you hadn't seen before. And so now to answer part A, it's real simple. It's S sub A is equal to V sub A times T, and V sub A is what? We were told that V sub A is equal to 2.7 meters per second times the T is 2 seconds, and again the seconds cancel from top and bottom, and we find that S sub A is equal to 1.4 meters. That's the arc length. And I'll spare us the S sub B is of course V sub B times T, and you can do all of fill in those blanks and you can see that S sub B is equal to 3 meters. Okay? So that completes part A. Now to do part B, we're going to look at the picture a little bit and try and figure some things out using some trig. Alright, so here is the picture replicated for us. We have our X and our Y axes, alright, there. And we have the origin. We know that the ordered pair of the origin is 0, 0. The place where particle A is at point, the ordered pair points X sub A comma Y sub A. Alright, so let's see what that is. X sub A, we could say, is that right there. And Y sub A is a little hard to show here because it's so tiny, but this is Y sub A. Okay, that little tiny amount there. Notice that this right here is your radial dimension R. Notice too that this is what we were calling our angular measure theta sub A, which incidentally is going to be this angle. And why is that? We've talked about this in a previous video. That's because they're alternate interior angles. That's a geometric argument, right? And by the same token, I can show here that this amount here, of course, particle B has ordered pair XB comma YB, and this right here is the XB, and this right here is the YB. Alright, and well, we said that this is theta B, so guess what? That right there is going to be theta B. Now that I've drawn all of this, notice that this is a right triangle, this is a right triangle. I can say by trig, I hope you will agree that X sub A is going to equal R, which is this guy right here. Right, this is R. This also is R. Okay, so R times, what is that? It's the sine of theta A. Alright, and so this is going to equal 5 times the sine of theta A. What about X sub B? Let's do that one. X sub B, this other guy up here, is going to equal, we got to be a little careful here, it's really going to be minus times R times the sine of theta B. Now you may say, why is it minus? It's because we chose to put our coordinates X and Y like that, And since we're going to the left relative to the x to get this x sub b, we know that it's got to be negative, okay? Now, what about y sub a? This little tiny distance right here sitting in there. What about that? I hope you would agree. Let me do this in a different color so you see it. I hope you would agree that it's got to be all of this radial amount r less this amount right here. Well, this amount right here is going to be r times, we said that xa is the sine, so this has to be the cosine of that. So I hope you will agree that y sub a is going to equal the total radial amount r less this amount right here. Okay, so less r cos of, I said theta b. This should have been theta a. I apologize, guys. This should have been theta a. Alright, so cos of theta a. Or put another way, we can factor out a common r and write this as 1 minus cos of theta a. Alright, and likewise y sub b, I'll spare us those details. You can see that this is going to be 1 minus cos of theta b. Alright, so, but where theta a is, we've already talked about this, it's s sub a over r. That's 1.4 meters over 5 meters. That is 0.28 rad, which is, we said that, it's 16.04 degrees. Theta b we did as well. It's SB over R is 3 over 5. It's 0.6 rad, which in degrees is 34.377 degrees. Alright, and so position vector R sub A, I will denote using these pointy brackets, is going to be component xa comma ya. Well, that is 5 times the sine of 16.04 degrees, comma 5 times this big expression, 1 minus cos of 16.04 degrees. Close the pointy bracket. And r sub b vector is going to be x sub b comma y sub b is minus 5 sine of 34.377 degrees, comma 5 times the big expression, 1 minus cos of 34.377 degrees. Close the pointy bracket. And so if you crank all of this out on your calculator, I believe you will see that our A vector is 1.38 comma 0.1947, and these components are in units of meters. Likewise, R sub B is going to be, the R sub B vector is going to be minus 2.82 comma 0.8733 in terms of meters as well. Okay, so that answers part B, and part C is actually not too bad at all. Okay, part C, you do need to know a little something about vectors, so I'm going to draw a little schematic so that we make sure that we're all on the same page. Here is the origin, O. By definition, the position vector RA goes from the origin out to particle A. Let's say here is where particle A is. So this guy, this vector right here, is in fact your RA. Likewise, your RB is going to be a vector that does something like this. Goes from the origin, so that's where the tail is. The head is pointing right at particle B. Well, you may say, what's so special about that? Well, if you've studied something about vectors, you know that the vector going between particle B and A, as I'm drawing in the pink right now, tail at B, head at A, is going to be this vector R sub AB. And if I can find what my R sub AB is, then I just find its magnitude and I have the distance between those two particles A and B. Well, what is R sub AB vector? That is equal to, you know this from vector analysis, right? You've taken some of these vector analysis courses, whether it be in statics or what have you. And you know that it's going to be where the head of that vector is pointing is going to be the position vector R sub A minus where its tail is, and that's position vector R sub B. This is by definition. And well, let's do that. We have R sub A, we just found it, it's 1.38 comma 0.1947. That's our A vector minus the R sub B vector. We just found that. The R sub B vector is minus 2.82 comma 0.8733. Let's do that. Well, that's real simple to do. So you see that R sub AB vector is equal to the vector 4.205 comma minus 0.6786. And again, this is in meters, but we weren't being asked to find that vector. We found that vector to find its magnitude, and so therefore the magnitude of that vector, again, if you know, if you've taken some vector analysis or statics class, you know exactly what I'm talking about. This we can find by the Pythagorean theorem. It's going to be the square root of the sum of the squares. We've also done this many, many, many times. So this is nothing new. It's going to be the square root of 4.205 squared plus, excuse me, minus 0.6786 squared. And when you do that, you find that the distance between those two guys is the magnitude RAB, and that works out to being 4.259 meters, and that basically completes what we were asked to find. So in summary, let's just go back real fast and say, just to summarize here, we wanted to find three things: the displacements, the position vectors, and the shortest distance between those two particles traveling in that circular path going in opposite directions. We did this circuitous discussion where we used some arguments from kinematics and geometry and also dimensional analysis, and we were able to come up with something that you probably could have jumped right into from the very get-go, just knowing basic physics, and done that. But I wanted to be sure that we're all on the same page with some of this circular motion concepts and the physics behind it. All right, we found the arc lengths SA and SB of those particles. We used some trigonometry, and we drew the picture again and used some basic trig concepts. And drawing the picture carefully, we were able to find all of those components. Let's say x comma a and x sub a comma y sub a. Those ordered pairs for particle A and likewise for particle B. Then we could use what we did up above to find our angles, and once we had our angles, we plug it into the trigonometric relationships up above. We find our XA and YA, and then we get our vectors. Once we have our vectors, we showed from a simple vector picture here what the vector R sub AB is, and then using the Pythagorean's result over here, we can take the square root of the sum of the squares of those components and find its magnitude, and that is in fact the distance between the two particles at exactly identically 2 seconds of travel. All right, my friends, thank you for bearing with me. I hope to see you in a future video.